This is going to be a short Ian's guide on visualizing the Laplace transform. So essentially what we can do is we can model this e to the negative t times sine t in the frequency domain using some handy MATLAB functions. So we can start out by defining some symbolic variables, s and t real. Now in MATLAB you can use symbolic equations, which end up looking like this. It's a nicer way of formatting equations, but you can also do more handy things such as taking partial derivatives or, for example, Laplace transformations. So we can actually define this equation using the Laplace transformation. So we can essentially write out exp negative t real times sine of t real, and then we'll essentially define our time variable t real, and then define our frequency domain variable s. And then we can visualize that here, so it'll be 1 divided by s plus 1 squared plus 1. And then what we can do is we can use this handy function called part frac. And essentially what part frac does is it's partial fractions. So like the k1 over some root plus k2 over some root plus k3, on and on and on. Now for this example, it's nothing too crazy, it's just multiplying out and adding 1, but if we get more complex examples, it'll actually do that partial fraction for us, so it'll save a lot of time. Now what we want to do real quick is we want to find out what the poles of our Laplace transform is going to be. So we can essentially take the coefficients, so 1 and then 2 and then 2, and we can essentially make an array here and then use roots to find out what our roots are going to be. So essentially the poles are going to be -1 plus minus the imaginary number I or j, depending on if you're in ECE or aerospace, same thing. But anyways, what we can then do is we can define our function up here as an anonymous function. Now you can solve your symbolic equations using the solve function, but it tends to be a lot more costly in terms of time. And since this is a quick video, we want to make this as quick as possible. So we're doing an anonymous function. But then what we can do is we can essentially define x and y as a mesh grid. Now a mesh grid is a handy function for three-dimensional spaces if you're doing like 3D surface plots, where essentially we're going from -10 and 0.2 intervals all the way up to 10, and we're essentially doing that for x and y. And then what we can do is we can define s, a part of our Laplace transform, where s is equal to some real value x plus 1 times an imaginary number j times y. And then what we can do is we can predefine z as zeros, the size of x, so it'll be the same size, just to save some memory so it's not changing every single iteration. And then we can say z, and then we can essentially pull our anonymous function up here, xs, and then plug in our s values. Because then what we can do is we can plot out what our Laplace transform actually looks like. And what's pretty cool is, so before we said that our poles here were going to be -1 plus or minus I. Well, on our real axis here, if we were to rotate to -1, we can see that's where our poles are aligned. And essentially these are shooting all the way up to infinity. But since I'm using only 0.2 as my my resolution, it's essentially going to be not as accurate. So it's essentially, you can imagine you just go to like 0.01, 001, and on as your step size. It'll get more and more accurate, and you'll see this get higher and higher up the screen. But anyways, for our poles, so -1 plus or minus I. So on the real axis, -1 lined up, and then on the imaginary axis, if I rotate here, then we can see we have 1 at positive I and 1 at negative I. So this is essentially a nice way to visualize your Laplace transformations. And for more complex Laplace transformations, you can use pretty much the same method above to essentially plot them out and get a better idea of what it actually looks like.